Hello students, in this lecture we'll discuss general theorems for the function which are differentiable in open interval and continuous in the closed interval. In the previous class or first two class, you have discussed the application of Rolle's theorem on trigonometric functions, trigonometric and for exponential logarithmic functions. Now we apply these theorems not on rules but other theorems on the functions and derive some results based on them, or we will verify whether the given function satisfy in the given interval, closed open interval, that the function are satisfied, the theorems are satisfied, and what results we will conclude if the theorem satisfy the functions in those intervals. So, first of all, let's today we'll drive the proof of the we'll drive proof of the Rolle's theorem and what is geometrical integration, and then in the successive lecture, next lecture, we'll discuss the application of the Rolle's theorem on different kind of functions, polynomial, rational, geometric, logarithmic, etc. What those functions which you have studied in the first class. Let's know the definition statement of the theorem. If a function fx, function of x, y is equal to fx the function, is defined in a closed interval AB, and number one, it is continuous in the closed interval AB, differential in the open interval AB, and fa is equal to fb. At the endpoints, so a and b of the interval, the function have the equal values. Then there exists at least one real number c belonging to AB such that f dash c is equal to 0. Now, two cases will arise. First, either fx is a constant function or fx is not a constant function. Now, case first is if fx is a constant function in this interval or in the whole interval, or this interval or this is subject of domain of function. If f is constant, its derivative will be 0 for all x. If it is 0 for all x, then it will be all x belongs to, or for all x of the domain, it will be, this is AB interval is subject to domain, therefore b f dash x will be 0 for x belongs to this closed interval AB. This implies that C belongs in the control AB exclude the endpoints A and B such that because fa is constant, f is constant, that is obviously 0. So here we concluded that is the point C belongs to interval f dash is equal to 0. Like this. Now, second case, fx is not a constant function in this interval, closed interval. Then as fx is continuous function in the closed interval AB, given fx is constant function in the closed interval AB, then fx is continuous in the closed interval AB, or all x belongs to closed interval AB. So if fx is continuous in the closed interval AB, this implies fx is bounded in closed interval AB. Means if f is continuous, at each point of the closed interval AB, fx have finite value. So means how many real value between a and b this interval have? We are dealing with real valued function. Between a and b, we have infinite number of real numbers, and a is also included in this interval, b is also included in this interval. So the function will take all the values, image of all the values belonging to the closed interval. Therefore, fx is bounded in this. If fx is bounded in closed interval, means we can obtain this reciprocal bond and principal bond. Means if fx is bounded, it will have its smallest value and largest value. So we can find this bond and this bond is square. Because f is not continuous in this interval AB, f is not a constant function. Therefore, at least one of these bonds, either a reciprocal bond or bridge bond, the reciprocal bond or greatest bond must be different from the equal values of fa and f, because is not a constant. The constant value will be could be equal to mm, equal at all points of interval. So, different must have different from x. That this bond is obtained that this bond is obtained at x equals c. Like either maximum value or minima is obtained at x equals c belongs to the open interval. Why open interval? Because value at a and b they are constant. Now, without any without any loss of generality, we assume that least upper bound is obtained by the principle. This thing will be clear when we discuss vertical integration of this term. Without loss of generality, we assume that this upper bound is obtained at x equals c. So means the if x belongs to c, c belongs to the particular AB, and is the least of the upper bound. This is least of the upper bound. Then for all x belongs to particular AB, fc will be the largest value. Therefore, fc plus h in the neighborhood of c, fc plus h will be less than or equal to fc, where c plus h is any point in the neighborhood of c. By the left neighborhood, if c is negative, in the left neighborhood, if c positive, sorry, if h is negative, in the left neighborhood of c, if h is positive, in the right neighborhood, b means c is the largest in the neighborhood of c for h being positive. So now let's discuss them. So if now suppose h is positive, we are discussing the right neighborhood. If h is positive, then if you take this thing to the left hand side, fc plus h minus fc plus h minus fc will be less than 0. If we divide an equality with positive number, equality will be the same. If this is less than this, then fc plus h minus fc less than 0 from this. Now, if we divide this inequality by h, positive number equality is the same. Now, taking the limit h to 0 of fxc plus h minus fc upon h less than 0. This implies right hand derivative at c is less than 0. Similarly, if we divide c plus h minus sc, which is less than 0 by a negative number equal to reverse, it will become greater than 0. Now taking the limit of this as h equals to 0, actually means we are discussing the left hand. So this will become, what will this become? Where h is approaching 0 from h less than 0 means x is approaching c from negative. So this implies left hand derivative of f at c is 0. So a and b. Therefore, f is differentiable in. We are given that f is because f is differentiable in the printable AB. This implies f dash exists for all exponents of printable AB. Implies f dash c exists for c belongs to printable AB. Now a, b, and c implies this exists. When will this f derivative at c exist? This will exist if only left hand derivative at c is equal to left hand derivative at c is equal to right hand derivative is equal to both are equal and equal to the derivative function at c. So when will this equation hold true? Right, left hand derivative is greater than 0, right hand derivative at c is less than 0. This will hold true if left hand derivative right hand derivative is equal to 0. This implies f plus c equals 0. 0 is a common value of left hand derivative and right hand derivative at c. So this implies f dash c equals 0 for some c belonging to the open domain. Now let us discuss the geometrical interpretation of the rules. Now let's draw. Let AB be is the graph of the function y equal to x. As the diagram shows that f is continuous in the closed interval AB, given as fx is differentiable in open interval AB, given. Therefore, the graph of fx have unique tangent at every point between them. As fx is differentiable in open interval AB, If you differentiate a function at any point of the interval, means if this is can be a finite value, means derivative if you differentiate function at any point, that is the slope of the tangent at that point. Therefore, the graph of function fx has unique tangent at every point within the end. Now let's see the graph. This is a function. Suppose this is a function a to b, depending on to b, and this is a graph of function a to b, this is a to b, and content means the we are flipping a pen, we will draw graph of it. So move that. So differentiate means at every point, differentiate particularly means at every point including excluding a and b, between a and b, and this function have unit tangents. Means so tangent will be unique. This function or this function or this is a maxima, this is a bound, this is a greatest bound, this is a local maxima, this is maxima, this greatest bound, this is this upper bound, this is local maxima, local minimum, and it's like that. So from these three diagrams, we come to the conclusion that if function is not a constant function, for which f a is equal to fb, for which f a is equal to fb implies what is implies? This implies m is equal to this implies m is equal to mb. M is equal to mb. F is equal f is equal to b implies m is equal to mb. M is equal to mb. M is equal to mb. That is ordinates are equal. Ordinates y coordinates are equal for that is where this or this means the y is the fx ordinates. From the above diagram, it is clear that there is at least one point. In this case, this point. See, this case, this point. In this case, we have three, more than three one point. This, or this. We can have this point of minimum. At least one point P on the curve between A and B, such that between A and B, such that the tangent is parallel to the axis. Therefore, the slope of the tangent is zero. So then zero means derivative. This is point. Let's see the point belonging to the open to AB. The slope is zero means derivative. First derivative at the point is zero. So function, if you differentiate function at any point, that will be the slope tangent at that point. Means we will have a point in the open to AB at which the tangent to parallax is. So